Hello all, today we are going to see a question from GATE 2017 Mechanical Paper 1, question number 39. So an initially stress-free massless elastic beam of length L and circular cross-section with the diameter D, but D is very much less than the length, is held fixed between two walls as shown here. So the beam material has Young's modulus E and coefficient of thermal expansion alpha. If the beam is slowly and uniformly heated, what is the temperature rise required to cause the beam to buckle is proportional to. So basically what they are trying to say is, if the beam is slowly and uniformly heated, so the temperature change that is occurring will cause buckling in this particular system because they are fixed at both ends. So that means during this buckling process, what is the temperature rise a function of, like what is its value basically. Okay, so before going into the problem, if you want to know more details about this particular concept of buckling and all, you can check out the NPTEL lecture Mechanics of Solids by Professor Priyanka Ghosh from IIT Kanpur. So let's go ahead with the problem. So if you have any temperature change of delta T, then your thermal stresses is given in this particular form, and in this particular case this is leading to a buckling of the beam. So if you have buckling, the critical buckling load is given in this particular formula if you have any rod which is being compressed. So let's see how to utilize these concepts into this particular problem. So now what is actually happening here? So you are basically giving some heat to the system and its temperature is rising by some delta T is the change in the temperature or the rise in the temperature. So because of this, the rod actually wants to expand in all direction. Okay, but it is fixed at both ends. So because of that, there are some stresses being induced. Okay, so now the assumption is that the beam is slowly heating and the buckling is happening due to this resistance. Okay, to this particular case. So resistance is happening from both sides because of uniform heating. So now let's assume that there is some load P because of which the rod might buckle. Okay, so let's find out that P. Okay, so basically according to Euler's theory, the critical buckling load is given in this particular form. Okay, so let's say that load is P where it is buckling. So that buckling load is given by this particular form. Okay, now what you have to find is like you have your stress due to temperature change is equal to E alpha into delta T. So now here the load is always in the axial direction, so therefore you can write your stress to be P by some area A, cross-sectional area A. So you can write it in this form. Therefore you can write your P to be again in this form, delta T. So now these two loads are the same because due to the heating the buckling is happening. Heating is causing the buckling. Therefore both are the part of same phenomena. So therefore you can equate these two loads. So now let's equate it. Therefore you can write pi square EI by L square is equal to E alpha A into delta T. E cancels, so finally you can write your delta T is equal to. So now you know that both the ends of the rod is fixed, therefore the length doesn't change. Therefore you can write your T delta T to be some let's say some coefficient C, where C is a constant. okay, into I by A. So basically your delta t is actually a function of I by A. Okay, so now what is I by A? I is actually pi by 64 d raised to 4, your moment of inertia, and your A is actually cross sectional area pi by 4 d square. So therefore this function you can write using this, that delta t is some function of these two ratio. So when you take these two ratio, pi by 64 d raised to 4 by pi by 4 d square. So now you can rewrite this whole thing as delta t is, let's say, some another function g of these constants you can take out, like that I'm writing it here. So some function of d raised to 4 by d square, that is again some function of d square. So you can write that your delta t is actually a function of some d square. So this is your final answer. So let's look into the problem. You can see that your option B is the answer. Okay, so this question was very straightforward and very easy to solve, but here the understanding is always about how what is happening, that is the heating is related to the buckling in this particular case. So I hope you understood the problem. You can see the NPTEL lecture to understand these concepts more deeply. So thank you.